At the most physical level, a computer processor is a network of microscopic switches. It only understands high and low voltage, a reality represented by billions of ones and zeros. Software engineers cannot think at this scale. Attempting to write or read raw binary to build a modern application would take lifetimes and result in constant logic-breaking errors. Some systems use an interpreter, which translates code line by line while the program is running. However, this on-the-fly translation creates a performance bottleneck that makes it unsuitable for high-speed software. High-performance computing requires a different paradigm, a tool that translates the entire program into standalone, optimized machine code before it ever reaches the user. This creates a massive scaling problem. Today, the industry uses dozens of high-level languages like C++ and Rust, which must run on several different hardware architectures like x86 and ARM. Building a direct end-to-end translator for every possible combination of language and hardware is unmanageable. It would require engineers to write and maintain thousands of separate programs. To make modern computing possible, engineers had to develop a universal architecture that isolates the language being written from the hardware it runs on. The first half of this process is the front end. Its goal is to strip away human-readable text to find the pure mathematical logic hidden inside the code. It starts with lexical analysis. A scanner groups characters into tokens, like keywords or operators, and ruthlessly discards spaces and comments. In syntax analysis, the compiler arranges these tokens into a grammatical hierarchy known as an abstract syntax tree. Finally, semantic analysis checks this tree for logical violations. It ensures the programmer isn't trying to perform impossible math, such as multiplying a number by a word. By the time the front end is finished, it has acted as a logical gauntlet, proving the code is sound before the machine executes it. Despite this rigorous checking, the front end does not actually produce machine code. Instead, it translates logic into an intermediate representation, or IR. This acts as a central hub between software and hardware. Since any language translates into IR and any hardware reads it, this design simplifies the scaling problem from a two-step process. This architecture makes the system modular. You can update a programming language or invent a new microchip without rewriting the entire software ecosystem. The final transformation happens in the backend, which maps the universal logic of the IR onto the physical reality of a specific CPU. First, the compiler performs code optimization. It acts as a ruthless editor, deleting dead code and pre-calculating constants to ensure maximum speed. Then, in code generation, the compiler maps these instructions to the physical constraints of the target hardware. This step allocates physical hardware registers, outputting the final binary assembly required for a specific family of processors. The backend ensures the programmer's logic is translated into the most efficient sequence possible for that specific chip's atomic structure. The result of this entire pipeline is a standalone binary executable file. Once this file is built, the compiler's work is done. The executable runs entirely independent of the factory of software that created it. This leads to a paradox. If a compiler is required to translate code to build programs, what program built the very first compiler? Early engineers solved this through bootstrapping. They used primitive, grueling languages to write basic compilers, which then compiled more advanced versions of themselves. Compilers are the tools that built the tools. By standardizing how human thought becomes physical electrical impulses, this architecture serves as the bedrock for the infinite complexity of modern software.